It's fine. I just, no, I've got it. All right, everybody. All right, everybody. Can you guys hear me in the back? All right, everybody. Welcome to another great See and Learn. We are going to get started in just a moment. So grab your drinks, find your seats, and please listen up as we start. We got two speakers for you tonight, so a lot in store. All right? How are we doing tonight? Pretty good? Okay, that was really terrible. How are we doing tonight? There we go, guys. Welcome to another awesome See and Learn event. As always, my name is JJ, and we've got a lot in store for you guys today. So I'm going to get started by thanking some of the sponsors that make all of this possible. So the very first is Carib Trans. They sponsor the live streaming. So we do stream on Facebook every time we do this, and you guys can go back and rewatch any of the events on Facebook or on YouTube. Or if you can't make it here in person, then you can watch them all online from your home or from wherever you are in the world. All right, so big thank you to those guys. El Momo is sponsoring our host for the evening. So can we give a big round of applause for El Momo? Awesome. Thank you so much to them. And of course, none of this would be possible without the Prince Bernhard Culture Funds and public entity SEBA. They do a lot for us every year, so big round of applause to those guys. And of course, to all of these sponsors and all the people that are here on SEBA. It takes a lot of work from a lot of different people for this to happen every single year, so big round of applause to all those guys. We've got a lot of sponsors, and if you guys want to help out See and Learn, there's a few ways. You could do some raffle tickets, which I'll get into in a minute, or you could talk to Lynn about being one of our major sponsors, like all these guys up here, all right? It's what helps See and Learn happen every single year. Now, the raffle tickets that we have got going on this year, we've got some pretty great prizes, and our drawing is coming up very soon, all right? We'll be drawing on the final night, so buy your raffle tickets while you can. We've got an indigo throw. We've got some handmade jewelry, some beauty products from Sabin Rock Living. There are several cottages and villas that are all giving away 3-night stays. So that is really awesome. There's Edie Witter's new book, Below the Edge of Darkness. It's a signed copy, so that's pretty awesome. There's a glassmaking class with Jo Bean. If you've ever met Jo Bean, she's fantastic. If you haven't, maybe it's a good excuse to. We have a handmade knife from John. We've got a guided hike from SCF and an 8-day, 7-night live aboard the Ocean Explorer. All right, those are crazy value in all of those for just $5 raffle tickets. So definitely get out there, buy some, and help support See and Learn. Now, some upcoming events that we have. Sunday, so tomorrow, the 24th, we are doing a constellation tour with your speaker tonight. Okay, so if you're pretty interested in what you're hearing and you'd like to know more about the night sky, then just come out with us. We're going to have a pretty big group. We got a lot of people signed up already, but we're taking anybody and everybody. So come out with us to Wells Bay Road, and it will be pretty awesome. On Monday, we have a dive with Andy Cow. He is going to be one of our speakers for the final night, so definitely come out and look for some of the cutest critters in the ocean. You'll hear more about that if you come to this talk. And on the 25th, we have the Mystery of Marine Litter presentation with Carolyn. I think Carolyn is actually here tonight. Could you stand up real quick and give a big wave? Awesome. So definitely check out that. That is going to be at Brigadoon in just 2 days. All right. Now, big announcement. We are switching the night of our final night, okay? It is going to be on the 26th instead of the 27th. So that means the 25th we have a presentation, and on the 26th we have another presentation, all right? So definitely come out for that final event. That's going to be when we do the raffle. It's going to be a really big recap of everything that's been going on for the entire month. The field project is still at the same time, so if you had signed up for the other one, it's still going to be a dive that's on the same day at the same time, so definitely still come out for that. And tonight, we actually have 2 speakers. So the first one to start out is going to be Laura. So she has been studying tropic birds for a while and has been living on Saba for a few months while she's out here. She has agreed very graciously to come out here and just make the best of her time by talking to all of you guys out here. So can everybody give a big round of applause for Laura?
Well, thanks a lot for coming, everyone. Good evening, and thanks a lot to the See and Learn team for having me here, actually. Well, JJ already introduced me. I moved here in June, and I have a background in nature conservation, and I knew that Saba is a really unique place in terms of nature, so I wanted to make my stay here as useful as possible. And I got in contact with a tropic bird expert on Stacia. Her name is Hannah Madden. Some of you might know her. She gave a talk at See and Learn in 2019 about tropic birds. So I got in contact with her, and together we started a project on tropic birds here on Saba. And I'm doing this independently, but in close cooperation with her. And where do I there I have to go? Well, she has a foundation which is called Ecological Professionals on Stacia. So I'm doing this with her, but also with the Saba Conservation Foundation. And I'm really thankful for being able to do this project here. Well, as the title indicates, my project has something to do with food, and I hope I'm going to be able to prepare you for dinner a little bit. So let's talk about tropic birds. Actually, there are 3 different species in the world. There's the white-tailed tropic bird. There are approximately 200,000 breeding pairs of this species. And then we have the red-tailed tropic bird. There are 35,000 breeding pairs globally. And then we have the red-billed tropic bird, which is the largest of those species, but at the same time the least numerous, with 8,000 to 15,000 breeding pairs. And actually, this is the one we're going to talk about today, because that's the species that's breeding here on Saba. And it has you see these blue areas. That's actually its breeding range, which is extremely large. And of those 8,000 to 15,000 breeding pairs. Actually, 3,000 are breeding here in the Caribbean, which is a lot. Just to give you some background about this species, it is a medium-sized, long-lived seabird, meaning it has a wingspan of a meter approximately. They can get 30 years old or even older, we don't know yet. And they spend most of their time at sea. They only come to on land to reproduce. And when they reproduce, they like to do that in the most remote and inaccessible locations. So the nest in cavities under rocks, and whenever you see me on this island during the next couple of months, it's probably going to be somewhere under a rock. They lay one egg, they sit on that egg for 43 days, and then there's a little chick hatching that's going to be on the nest for another 85 days, which is an extremely large period of time for birds. And once they fledge, they fly off to sea, and then they stay there for the next couple of years. And they reach sexual maturity when they're about 5 years old, which is also quite late. Actually, on this photo, you see an adult with a red bit, and then a chick with a yellow bit. So it just gets bred when they are older. And I talked about these numbers, the 8,000 to 15,000 breeding pairs globally, but then looking at Statia and Sabre, we're actually in a tropic bird hotspot here. Statia and Sabre together support 13 to 25% of the global population. And then looking at the breeding pair numbers per island, Statia has approximately 400 breeding pairs, while Sabre, where these are estimates, again they nest on really inaccessible locations, but Sabre might support a population of 2,000 breeding pairs, which is really a lot for such a small island. And I think this definitely makes it Sabre's most iconic species. And it's not weird that we see this bird just in front of the SCS office. It's on the banner, and during every See and Learn opening presentation. So I'm really glad I got the chance to talk about this bird tonight. And we could fit this in. Well, unfortunately, it's not going that well with the population. There's many threats, and I just want to say this for seabirds in general. Actually, seabirds are the bird group that has the highest rates of population declines among all bird groups. And one of the major threats is introduced predators. These photos are actually from Sabre from 2013 from camera traps. It's a colony close to the gas station, and you see on the left picture there's a feral cat, on the right picture there's a black rat. So especially the colonies on the south side of the island have declined dramatically, mainly due to predation. And I think this is really important to mention, and that's why I included it. And these numbers, well, the population numbers should be monitored all the time, but this is not going to be the focus of my project, because there's other things we really don't know about these birds. As I mentioned, tropic birds spend most of the time at sea, and what we don't know is where they actually forage, how they move, when, what they feed on, and how this relates to environmental variables. So why is this knowledge actually important? It's important because we need to know if there are diet overlaps with fisheries, where there might be direct effects like bycatch, but also indirect effects when they target the same species, like fisheries. Probably tropic birds feed on small pelagic fish stocks, but then they might also be dependent on subsurface predators like tuna and mackerel. It's also important to know where the key foraging areas are and what's the protected status in those areas. And ultimately this can be used to incorporate the areas in management plans and start conservation initiatives. I just want to mention why we actually care about seabirds, where they make a lot of noise, they smell like fish, but they do have a key role in ecosystems. They actually forage over wide areas and directly influence terrestrial ecosystems by transporting marine matter to their breeding sites. And then they are also top predators. that regulate species at lower levels of the food chain. They are also really important indicators for ocean health. Actually, last year there was the first evidence of plastic ingestion by tropic birds on Statia. And they also serve as ecosystem indicators by monitoring population trends. You can get an idea of changes in marine ecosystems. And what is also important, they have a cultural value, where they are a tourist attraction for many people, but then they also have a cultural significance, and I think especially on an island like Saba, having such a huge population, this is really important. So I want to, does anyone have an idea what we see on this map? It's not about supermassive black holes yet, just forget about the black spot. Sort of. It's actually the foraging trips of 37 tropic birds from a breeding colony on Statia. Hannah Madden just conducted this foraging study, and she deployed GPS loggers on these birds. And she found out that they had an average distance, well, in terms of foraging trips, from the colony of 43 kilometers. But then there was even one bird that traveled a maximum distance of 334 kilometers. And he even covered almost 900 kilometers doing that. So on this map, you see Statia is somewhere under the red triangle, and you see that most birds foraged around Staba, Statia, St. Martin, St. Kitts, Montserrat, but some even traveled further. And based on this, Hannah also identified core foraging areas of red-billed tropic birds. And you can see it on this map. You could start counting now, but can you make a guess of how many countries they covered during their foraging trips? Well, it's actually 11 countries, which is, well, it's 11 exclusive economic zones. But then these areas fall primarily under the jurisdiction of the Netherlands, St. Kitts and Nevis, France, Venezuela, and the United Kingdom. So they definitely like to feed internationally. On this map, you see where there's Statia, again here, and then the dark green area is the area where most birds foraged, and the light blue area is the area where some birds traveled to, and some traveled even further than that into the light green area, which is the maximum space used by those birds. So you might think, okay, we have this knowledge, that's all we need to know. We can work with it. But then getting back to those numbers I talked about, the population on Statia is much smaller than on Saba. And we actually have indications that the birds from Statia and Saba don't exchange with each other, and even colonies might not exchange that much with each other. And there are also indications that the birds on Saba have a higher diversity of fish species they feed on. So the populations on Saba and Statia might have completely different foraging grounds and patterns. And that's why Hannah and me started replicating this project here on Saba, and thanks to Vogelbescherming Nederland and Prins Bernhard Cultuurfonds, this is possible. Ooh. It's flying off. And actually there are three main breeding locations or breeding colonies here on Saba, which is Tent, Great Level, close to the gas station, and Old Booby Hill, while Old Booby Hill is definitely the biggest colony of on this island, but at the same time the most challenging because you're constantly working just on the edge of a cliff, which makes field work much more fun. And I just want to give you an idea of what we started with during the past month. I just started with this project in October. And when I say we started doing this, I mean lots of volunteers who are helping a lot, and I wouldn't be able to do it without them. We've been searching and marking nests. We've been visiting the nest regularly to check the egg status, to know when the chicks are going to hatch, and to be able to determine if the nesting attempt was successful. And we also started banding birds to be able to identify the adults and also in the long term to be able to determine if birds exchange between colonies or even islands. And I said I'm going to prepare you for dinner, where we're also collecting regurgitates and hope that the fish is not digested that much already, so we are able to identify the fish species they had in their stomach. And from December on, or actually when most of the chicks start to hatch, you actually see a little fluffy snowball here. That's a really small chick, and we want to deploy the loggers within the first 3 weeks after hatching, because that's the time when the adults are constantly with the chicks, but also the time when they fly on and off from the colony most often. So we're going to deploy GPS loggers on the adults, and this is what they look like, and we're going to deploy them on the flight feathers of the tail, a method that Hannah has used successfully before. And actually, to wrap up and to return to the question, where do we eat today? We do know that tropic birds spend most of their time at sea, and we also know that birds of Statia like to dine internationally, and we expect Sabre's birds to do so too. But still, we really want to find out where that huge population on Sabre is having its key foraging areas. We're going to compare those results with Statia and hope to be able to assess whether especially protected areas of Caribbean importance are necessary for this bird. I really want to thank you for your attention, and I especially want to thank my advisor, Hannah. She's doing a great job in helping me, but also Michiel Boeken and Mardik and Hans from Wageningen, SCF for their practical support here on the island, the funders, and Vogeltrekstation for the permit to handle and ban birds. But especially I want to thank all the people here in Sabre who are helping and volunteering me. I really wouldn't be able to do this project without them. So thanks a lot. Are there any questions? Yes, it's you. Sure.
Do the tropic bird, do the breeding pairs breed every year?
So the question is if the tropic birds breed every year? Yes, once they have reached their sexual maturity, they breed every year. Sorry?
Once a year?
Once a year, one egg. Well, if the nest attempt, if they have a nest failure, they might relay an egg or try it again. Yeah.
So the tropic birds that we see around the island are probably breeding pairs that are nesting at the moment currently?
The question is if the tropic birds we see right now flying around the island are breeding on the island right now. Yes and no. Well, I think you can see tropic birds all year round, but there's also they have a breeding peak between January and April, but they might breed during the whole year. It's not synchronized anymore. It might have been in the past, I'm not sure about that. But you might also see birds flying around that might try to find a mate that might still be younger. But right now, I would say yes, the birds you see flying around are breeding here. Yes. Yes.
I'm still a little bit puzzled about the fact that you said they spend most of the time at sea. We know that. It's always been cold. But their average range, foraging range, is 43 kilometers. What are they doing in the meantime? I mean, 43 kilometers is nothing for a bird like this. Where are they going? What are they doing?
The question is, well, the average foraging trip was only 43 kilometers. And the question is, what are they doing in the meantime? Well, I hope we're going to find out. I'm not sure about that yet. But I guess not all foraging attempts are successful. So it's not that they just fly 40 kilometers, then they catch a fish, and that's it. And they also have to do that constantly, of course, to feed their chicks constantly. So it's not that they just do that once. They do it quite often. Yeah. Yes?
So the fish that you showed, they were like really intact. Do they even take computers, or is it mostly features, right? Or
the question is if the fish we saw from the diet sample, that was pretty intact. If they actually are able to digest it, yeah, they do swallow it in a hole, so they don't chew on it or anything. But then within the stomach, and I'm sure Eva could tell me more about that, how that actually works. But no, they do digest it, and what you saw that were regurgitates. So sometimes they might just throw up, and that's what we can collect then. Yeah.
They regurgitate to feed the chicks.
Yeah, also, but I think also sometimes they do it when they get stressed, or when they're handled. Well, that's not good for the bird, of course, but it's good information. Yeah. Any other questions? Okay. Thank you.
All right, guys, one more big round of applause for Laura for that awesome presentation. Thank you for coming out. And now, for our main speaker of the night. All right, so our presentation tonight extends further than Saba, further than the Caribbean, and even further than Earth. No matter where you are in the world, space is always around us. So John is here to give us some perspective on how much space is really out there. Now, John Della Costa is currently a graduate student at San Diego State University studying astronomy. He has a deep passion to educate anyone that is willing to listen, and he does many outreach programs, reaching over 1,000 students a semester during his planetarium shows, constellation tours, and telescope demonstrations. He's even started a charity that is called the Starbound Foundation, which brings astronomy to students all over America. I hope that everybody out here has found a chair, because you will want to be sitting down for this presentation. All right, so please give a big warm welcome to the astounding astronomer himself, John Della Costa.
Hello. Hello. Can you pass these out to people who didn't get any? Did everybody get their jelly beans? Oh, here's a cup too, if that helps. Everybody got their jelly beans going here? Cool. Did anybody get hungry and eat them? Yeah? Oh, we got a hand in the back all the way back. So you can hear me. That's a good sign. That's great. So speaking of tropical birds, is the clicker around? Thank you. That's all right. So speaking of tropical birds, black holes. I don't know. No, I mean, there's not a lot of overlap. I'm so sorry. There's not a lot of overlap. But so you might be wondering why some nerd is coming up to talk to you during See and Learn, right? But I like to think it's the other spelling of the word see, so S-E-E and learn, hopefully. And if you're able to, we're actually in a really perfect spot right now to talk about some planets. We're not going to talk about them now. It's a little bit of a preview, but if those clouds weren't there, you'd be able to see two bright dots. One of them is Jupiter, and one of them is Saturn. So throughout the talk, if you look back, if you get bored, and you look backwards and you look up, you might be able to see some planets for you, okay? So hopefully that happens. So my talk is, whoa, cool. So laser works, very cool. So I'm going to try to bring the black holes down to Saba, but not too close because that might hurt a little bit, as you'll see. But so the goal of this talk is to try to inform, educate, maybe blow some minds a little bit too, hopefully, and do maybe entertain a little bit as well. All right, so first off, where do black holes come from? All right, so black holes are actually the remnants of dead massive stars. So if you want to become a black hole, it's really simple. All you got to do is become a star, all right? But you have to be really kind of heavy. You got to be a really heavy star. So if you want to become a black hole at the end of your life, what you're going to have to do is become a star that is greater than 20 times the mass of our sun. 20 times the mass of our sun. Whoa, cockroaches, cool. So Do we have a cockroach expert coming to see and learn? No. So if you want to become a black hole at the end of your life, when you die, you're going to explode and you're going to become a black hole. All right. So this is what the explosion looks like. That's a massive star, and what's left over is a small black hole. Varying in sizes. It depends. This is a real Hubble Space Telescope image. I'm going to say it's an explosion, but it's really not. But that's kind of what explosions look like in space. But that's real Hubble Space Telescope data right there. So that's where black holes come from, right? But what even is a black hole? You might not even have any clue what a black hole is. So this is how I like to explain it, okay? So let's imagine we're on Earth. Let's imagine that, okay? We're all on Earth, all right? And you try to jump off the ground a little bit, all right? You try to jump off the ground. This guy's pretty good. He can jump fairly high, right? Let's double the mass of Earth, okay? Let's just double it. How high will this gentleman be able to jump at that point? Not quite. You're close, though. It's half. He'd be able to jump half as high. If the Earth weighed half as much, he would be able to jump half as high. Okay? So that line there. Now, what if I asked you, what would happen if we increased the Earth's mass by 1,000? Okay? How high could you jump if we increased the Earth's mass by 1,000? Yeah, you wouldn't be able to jump at all. In fact, you'd probably be about as flat as a pancake, right? You wouldn't be able to jump at all, okay? So this is actually how black holes work, all right? So light is trying to jump off the surface of a black hole, but it can't. It's just got too much mass and gravity. But it's not only about how much gravity you have, all right? It's also about how dense you are. So you can actually turn anything into a black hole, anything you'd want, okay? So you just have to make it dense enough. So you look pretty strong. Why don't you go ahead and try to crumple that piece of paper as tight as you can, okay? So for you folks at home, he's crumpling a piece of paper, all right? Okay, here we go. It's getting there. All right, it's okay. For you folks at home, it looks a little weak, I'll be honest. Let's get a stronger person here. Let me try that. Are you stronger, you think? Try and get that a little bit, trying to get that a little bit tighter, okay? All right, that looks pretty good to me. Thank you. Okay, so they crunched this piece of paper down. This is the smallest they could get it. Now, if you wanted to turn the Earth into a black hole, okay, you would have to take all of your friends, all of your family, everybody you've ever known, all the cars, all the land, all the water, and you'd have to crush it down to a size about this big in order for it to turn into a black hole. That's how dense black holes are. They're extremely dense objects. Hence, scientists this is how they would describe a black hole: an extremely compact object whose escape velocity is the speed of light. That is the scientific definition of a black hole. All right, which is why black holes look black, okay? They don't emit any light at all right? So that's what a black hole is. Does that make sense? Hopefully. So yeah, you'd have to crunch Earth down to this size if you wanted to turn into a black hole. A little bit crazy. All right. So, but just how massive are black holes, right? So when they're first born, they can be, anywhere from 10 suns, so the mass of 10 of our suns, okay? They can be, some can be smaller, but an average is about 10 when a star explodes into a supernova and the remnant object is a black hole. You can have about 10 stars, but the maximum that we know of, that we've actually discovered in space, can be over 1 billion suns, okay? So you can have 1 billion suns there, yeah. Hopefully that shows them a little bit. So black holes have an extremely wide range of masses that you can have, okay? Yeah, that's thank you. So black holes can have an extremely wide range of masses that they can inhabit. Anywhere from the tens to hundreds to the millions and billions of solar masses, so times the mass of the sun, okay? Believe it or not, we have not found any black holes that are like 50,000 solar masses. We're still looking for those. We're not sure why they don't exist, but that's ask me about that later if you want. Okay, so this is where the jelly beans come in, okay? So everybody, I want you to hold out that jelly bean in your hand, all right? Hold out that jelly bean and imagine, all right? Imagine that the Earth weighed as much as a jelly bean, all right? There you go. Sorry if it's melted. Yeah, sorry if you ate it already or if you didn't get one. But yeah, so imagine that let's all just imagine that the Earth weighed as much as that jelly bean in your hand, okay? How much, and this is some audience participation here, how much do you think the largest planet in our solar system, Jupiter, would weigh on that same scale if the Earth weighed as much as a jelly bean? Any guesses? 50,000 jelly beans? Okay, anything more, like, I don't know, anything like more tangible than 50,000 jelly beans?
150 million?
Okay, close? No. Any, like, objects you can think of? An elephant. Okay, an elephant. What was that?
Watermelon.
A watermelon. Okay, that's good. A house? Okay,
Okay,
anybody else? A car? Okay. Oh, a guitar. Okay, that's very good. So, if the Earth weighed as much as of that jelly bean, then Jupiter, the largest planet in the solar system, would weigh as much as a can of soup. All right, a can of soup. So kind of, pass that around if you want. I only got one can, so those of you in the back, it might take a second to get there. But so on that same scale, Jupiter would weigh as much as a can of soup. How about the sun? Can anybody get, on that same scale, can anybody tell me how much the sun might weigh on that same scale?
Watermelon.
A watermelon? Okay, there you go. He really likes watermelons. So anybody else? A what? A golf ball? Okay, anybody else? A bottle of water. Anybody else?
I'll go for the elephant.
An elephant again. Okay, 2 elephants. All right. Yeah. A what? A rock. Okay, a big rock or small rock? A big rock. Okay. So on this same scale, the sun if the Earth weighed as much as a jelly bean, the sun would weigh as much as, I think I'm pointing in the wrong direction, a motorcycle on that same scale as that jelly bean. Okay? Now, here's for the crazy, the cool one. Astronomers think that there's a black hole in the centers of most galaxies in the universe. Not every galaxy, but most galaxies have a black hole at the center of their galaxies. The one at the center of our galaxy is called Sagittarius A star. And on the talk tomorrow, I'll try to show you, if we can see, if the clouds are working with us, I'll try to show you the constellation Sagittarius and approximately where that black hole is. But, so the black hole at the center of our galaxy, what we're all orbiting around, okay? How much do you think that would weigh on the scale of Earth as a jelly bean? Any guesses? Elephant? I hear elephant again? Third time's the charm. A mountain, okay. What did you say? An elephant, okay. Seba, okay. Our sun, okay. So on that same scale, if the Earth weighed as much as a jelly bean, you think it'd weigh as much as the sun. Anybody in the back, any guesses?
They're asleep.
No?
People in their minds.
Okay, so I'll break the news to you, okay? So if the Earth weighed as much as a jelly bean, Jupiter weighed as much as a can of soup, the sun weighed as much as a motorcycle, the black hole at the center of our galaxy would weigh as much as the Pyramid of Giza, okay? On that same scale. The Pyramid of Giza. It's a pyramid in Egypt, if you don't know where Giza is. But really, really crazy, right? Really wild how massive black holes are, especially supermassive black holes at that. Now, but what's even crazier than that, okay, is that black holes, our black hole at the center of our galaxy, our black hole is actually a little baby black hole. It's actually really small compared to the other black holes in the universe. It's really tiny. Coincidentally, this is what a baby would look like if it were going into a black hole as well. Not having a good time. But also it would get spaghettified as well as it goes into a black hole. There's also a lot of other crazy things that happen near a black hole, like time slows down and light is bent around them. So ask me about that at the end. Keep your questions going in your head and ask me about that. But yeah, so our black hole is actually a really tiny black hole, okay? This, if you guys remember this picture, this is the first ever picture of a real black hole, okay? Taken with the EHT, the Event Horizon Telescope. A telescope that was literally, kind of not literally, but also kind of literally, the size of the Earth, okay? That's how big your telescope has to be in order to get resolutions this high, okay? So the telescope was the size of the Earth. Ask me how they did that later. It's kind of like magic, actually. But so this is the picture of the black hole. This is the black hole in the very center there. This is the accretion disk around it. We'll talk more about the accretion disk. That's actually what I study. So that's the black hole. And just to give you a sense of how large this black hole is, okay, I I keep pointing in the wrong direction. This is the sun, and that is Pluto. Okay, one of the farthest away objects in the whole solar system, and that's Voyager 1, launched in 1960s, fastest object, that man-made object, and it's still just streaming out of our solar system. It just reached the edge of our solar system, I think, a couple of years ago. But this is how big that black hole is. Okay, incredibly, incredibly crazy. It's about so our black hole, the center of our galaxy, is about 4 million solar masses, so 4 million solar masses. This black hole is about 6 billion solar masses, 6 billion times the mass of our sun. And we would fit right inside of it real nice and easy. So you don't want this one coming towards us anytime soon. We'll get swallowed basically whole. But on that same scale, as the Earth as a jelly bean, that black hole would weigh approximately as much as Mount Everest on that, which is a lot. If you don't know how much Mount Everest weighs, it's a lot, okay? So quite, yeah, it's a big mountain, yeah. So yeah, this black hole, and this isn't even the largest one. We think some black holes can get up to 50 billion or more, 50 billion. This one's only 6 billion, so 50 billion is even crazier as well. So some of you might be asking though, right, like how can I study black holes, right? They're black, they don't emit any light, right? So how can I study something that I can't see, right? It's a good question. So what I actually study are these, like I told you before, these things called accretion disks. So they're around some black holes. When an object or a star or a planet or a big ball of gas gets really close to a black hole, it doesn't just get sucked in and swallowed in by the black hole. What happens is that the material from that object falling in creates a disk around the black hole and kind of gets funneled like water going down a drain into the black hole. Now, what happens in that accretion disk is that this matter towards the black hole, matter closer to the black hole, orbits faster than the material farther away from the black hole. And so what happens is you get fast-moving particles rubbing up against really slow-moving particles. And what happens is you get a lot of friction, all right? You get a whole bunch of friction, all right? So in accretion disks, there's a lot of friction. And when things heat up, they start emitting light, hence like light bulbs, right? As you pump more and more energy into a light bulb, it looks redder and then white, and eventually, if you put enough energy into a light bulb, it will look blue. The same happens with an accretion disk. As the accretion disk heats up from all that friction, it starts to emit light. And it's actually that light that I study. That light coming from the accretion disk, not from the black hole, but coming from the accretion disk of a black hole. But that light can tell you many, many things about a black hole, like its mass, what it's made of, and a bunch of, and how, it's crazy, a bunch of other things. It's really amazing what you can get from just studying the light coming from these accretion disks. Now this thing here is called the jet. I won't go into it a lot, but if you have a question about the jet, ask me after. It's kind of complicated, but it's not coming from the black hole, it's also coming from the accretion disk. And some black holes have jets around them as well. Okay, so this is what a black hole, we think what a black hole would look like if you were right next to it. Okay, if you were standing right next to it, which you don't want to do, but if you were standing right next to it, this is approximately what it would look like. You can see there's like a disk here, but a disk here. What I showed you before was a ball and a disk like this, but now what you're seeing is like this and like this, right? It's weird. That is due to the gravitational warping effect that black holes have. They have so much mass and so much gravity that they actually bend the fabric of space-time around them. And so when you're near one, it's kind of trippy looking. The light from the accretion disk actually looks, basically we think like that, and it's kind of, again, it's trippy. So this is what it looks like from really close up. But this is what, so before we talk about that, can anybody tell me what these two pictures are an object? What are they? Tell me what they are. What do they look like to you? No? Well, I heard somebody say it over here. Stars. Yeah, these look like stars, right? So that star right there is actually Sirius, all right? Yeah. Okay, so that star right there is Sirius. It's the brightest star in the entire night sky. We might not be able to see it tomorrow night when we're, I'm looking for Jupiter and Saturn. I think the clouds are still there. But we might not be able to see it tomorrow night, but it is about 9 light years away, and it's the brightest star in the entire night sky. A lot of people think the North Star is the brightest star in the night sky, but it's not. It's actually Sirius. Now, so that's what Sirius looks like. Now this star, actually I'm kidding, I lied to you. This is actually a quasar. So that is actually a black hole called 3C273, okay? It's the first quasar, quasi-stellar object. It looks like a star, right? It's because, the reason why it looks like this is because it's extremely bright, okay? It's extremely bright, all right? It's one of the brightest non-galactic sources that we know, actually. And that object is actually 2.5 billion light years away, okay? Just for those of you who don't know what a light year is, 1 light year is actually a unit of distance, not time, okay? So 1 light year is the distance that light travels in a year. And light travels approximately 300,000 kilometers a second, about 6 times around the Earth, maybe 7 in 1 second, to the moon and back in 2 seconds. And 1 light year is equal to about 6 trillion miles. 6 trillion miles. I can't convert that to kilometers for you right now, but 300,000 times a year, and then you're there you go. Okay, but so Sirius is 9 light years away, so it takes the light from Sirius 9 years to get to us. But this object is 2.5 billion light years away, meaning the light from that black hole took 2.5 billion years to get to us, from it to Earth, okay? But you can see, even though it's way farther away than Sirius, it's still extremely bright. It's still extremely bright. How is that possible? How can something be so bright so far away? And that's because it's actually a black hole with that accretion disk orbiting around it. It's so hot. That accretion disk is so hot, and that black hole is so big, and the accretion disk is so big that it emits an immense amount of light, okay? An immense amount of light. And we can see that from across the universe. And this is the closest quasar to us, okay? Some quasars are bright enough to where we can actually see them from 13 billion light years away. And if you don't know what that is, 13 billion light years is approximately the age of the universe. So we can see black holes that were around very close to the beginning of the universe, okay? So these things are extremely, extremely bright, and I study those things called quasars as well. All right, so you can see them, right? So I can see them, but where can I look at them from, right? Well, so you might be wondering, so this is Saba right here. This is Mount Scenery. I actually just walked up it today. It was quite a hike. If you haven't yet, it's really magical going up there, but bring a lot of water. But so this is Mount Scenery on Saba, right? So the first thing, it's a little bit weird, but the first thing that I noticed on Saba was that I didn't see this, okay, that right there. For those of you in the back, that's a telescope dome, all right? So when I came to Saba first, I was looking at the top, and I was like, where's the telescopes, man? But it makes sense why there are no telescopes on Saba. And that is because you might think, well, it's a really high mountain, right? It's really, really high. And astronomers really love the height of mountains. That's why we put telescopes on the top of mountains. It's because we get above a lot of atmosphere. There's a lot of atmosphere near the sea, and that atmosphere causes stars to twinkle, all right? And that's what the atmosphere is what causes stars to twinkle. And if you can get above a lot of that atmosphere, stars will twinkle less. And your images taken of the sky will look less blurry over time, okay? So you might be wondering, why don't you see any of that? So it's high, though, but it's also extremely wet, okay? It's really, really wet, and as you know, there are clouds there very often, and so it rains quite a lot. Astronomers hate water, all right? They really hate water. They like telescopes to be high and dry, okay? So why we don't see any telescopes on Saba is because it's very, very wet. That water makes the stars twinkle even more. So it's like taking a picture with like a 2005 Nokia versus an iPhone 11 today or something. The images look way better on an iPhone 11 versus that Nokia, and that's basically what you get if you go to a dry and high place, much like this observatory here, which is called Cerro Tololo. It's in Chile, the country, not the food, and so it's on the top of a mountain in the Atacama Desert. So it's one of the highest, it's one of the driest places on Earth, but it's also very, very high on the top of a mountain, all right? And these are some really beautiful telescopes, just amazing, at sunset, really, really beautiful. Just to talk a little bit more about telescopes, one telescope that I'm really looking forward to is called the Large Synoptic Survey Telescope, LSST, okay? And so this is actually how much of it is built right now. It's amazing because like a couple of years ago they had nothing here. So they're really working quickly on this telescope, and this is what it's gonna look like when it's finished. It's an extremely large telescope, but what makes it unique is that it actually is going to take an image of the sky, the entire sky, every 3 days. And so you will be able to actually watch a movie of the entire sky. And this is actually very helpful for my research because I study black holes by taking images of them over and over and over again over long periods of time. And so this survey is going to run for 10 years and get a picture of the sky every 3 nights. Okay, that's going to be a lot of frames in your movie. So one day you all will actually be able to watch a movie, an actual movie of the entire sky, stars exploding, black holes being formed, black holes varying in their brightness, which is what I study, asteroids, planets going in front of stars. So this telescope is really, really going to be amazing for astronomy when it comes online, and it's scheduled to come online in the next 2 years. So I'm really excited for that as well. So back to SEBA though. So this is SEBA, right? And so we're actually going, I think, to the west side of the island for our talk tomorrow. But SEBA, so you may not be able to, build a telescope, a really big telescope on SEBA. But the unique thing about SEBA is that it's actually really, really dark. Okay, you can see the Milky Way galaxy, and we'll hopefully be able to see the Milky Way tomorrow night as well. But you can actually see the Milky Way from SEBA. This next image is a picture of light pollution. Okay, it's a picture of light pollution in the Caribbean. So this is Puerto Rico. That's St. Martin, and right there is SEBA. Okay, so as you can see, the redder and whiter means really bad. Okay, and this grayish bluish means fantastic, okay? So SEBA, you might not be able to build a telescope on it, but you get some of the darkest skies in not only the Caribbean, but in the world, okay? So that's really the most unique thing about SEBA. It's seriously one of the darkest places in the entire Caribbean. So if you come out tomorrow night, it's gonna be really dark, so bring a flashlight, but try not to shine it too much. But yeah, it's gonna be super duper dark. All right, and speaking of which, that talk tomorrow is at 8 p.m., and I think we're meeting here. Is that right? Meeting here, and we're all going to get taxied, I believe. Whoa, that's cool. So come out to that. And I just wanted to thank See and Learn very much for having me so much. Thank you. Does anybody have any questions? I'll leave it on this slide here. Are there any questions? Yeah, back in the back.
Why don't you find black holes with a mass of 50,000 suns?
Oh boy. So I was hoping you wouldn't remember. I asked you to tell me that. So we're not entirely sure. So we know that black holes that are tens of solar masses come from dying stars. And we know that the black holes at centers of galaxies, how they got so massive was that they ate a lot of things, okay? So the mass if you take a solar mass star and throw it into a black hole, that black hole will now weigh one more solar mass, okay? That's JWST, by the way, if you were wondering. So, but those are called intermediate mass black holes, okay? And so they're like 10,000 suns. We've not discovered those yet, and we think it's because the only way that black holes can get bigger is they either merge with another black hole, and create gravitational waves, if you guys have heard of those, or is to eat more things. And we just don't think that black holes are able to eat that much that quickly for us to actually see them. So we don't actually see those intermediate mass black holes, but we're looking, all right? We're looking. We'll let you know when we find them, okay? All right, any more questions? Oh boy, I saw your hand first. Somebody. Yeah.
How many light years is the closest black hole to us?
How many light years is the closest black hole to us? That's a fantastic question. I think it's about Oh boy, don't quote me on it because I'm not sure, but it's about 500 light years. So it's really, really far away. Yeah, if a black hole came to us, even if it was a small one, in fact, small ones are kind of safer than the big ones, believe it or not. But even if it were a small black hole and it came near us, it would be a bad day for us if that were to happen. So luckily, the nearest black hole to us is really far away. In our galaxy, though, but really far away. Cool. Your question.
Yeah, if black holes are formed at the end of a star's life, and we can see one that's 13 billion years away, and that's the age of the universe.
So the question was, if we can see black holes, they come from the dying stars, right? How can we see black holes that are really close to the beginning of the universe when there were no stars? Okay, that's a fantastic question. And we think that in the beginning of the universe, one of the ways that these supermassive black holes formed, it's not confirmed yet, that's one of the things that I'll be studying and trying to figure out. But we think in the beginning of the universe that there were these immense clouds of gas and dust. Immense, huge, huge clouds of gas and dust. And that's what stars form out of, is big clouds of gas and dust. But some of those clouds of gas and dust were so huge that they skipped the star part. They totally skipped the star part and went right to a black hole. All right? And that's how we think those supermassive black holes in the beginning of the universe formed, and how they formed so quickly after the beginning of the universe. So great question. Yes? Good question. So do black holes ever die? Black holes ever die? So there's this guy named Stephen Hawking, if you ever heard of him. And he came up with this thing called Hawking radiation, and it's like basically if you left water out on the ground in the sun, it would evaporate. The same thing kind of happens to black holes, although like even a 10 solar mass black hole would take a billion years or billions and billions and billions of years in order to evaporate fully. Okay, so it takes a really, really long time, and we think that's happening. That has not been confirmed yet, but we think that's actually happening. Yes, ma'am?
You were talking about a black hole that there also time is different or changing.
Yeah.
What do you mean?
So near a black hole, and I like this analogy. Let me know if it works or not. But near a black hole, the fabric of space-time is bent so much that it actually changes how time works near it. Okay? So time runs slower near a black hole. And here's the best analogy that I can give you. So imagine that I'm taking a video of a ball rolling down a hill, all right? As I take that video, that ball is going to speed up and get faster and faster as it rolls down the hill, right? Now let's imagine that ball is light, okay? Light, though, doesn't speed up, okay? It's a universal law, actually, that Einstein discovered, a universal law that the speed of light always has to stay the same, okay? So much like a bowling ball on a trampoline, black holes make dents in the fabric of space-time. And if a photon were to go down one of those hills, okay, what would happen? You'd like to think it would speed up, right? But if I'm recording that photon going down that hill, it can't change its speed. It has to stay at the same speed, okay? So how do you make that ball or that photon stay at the same speed? Well, you'd slow time down on your camera, right? And so the ball would look like it's always at a constant speed as it's going down the hill if you progressively slow time down as you get closer to the bottom of the hill. Does that make sense? So no, okay. So the analogy didn't work, okay? So basically, all you need to know is that close to a black hole, time slows down, okay? And it's because of this thing called, it warps the fabric of space-time. The speed of light always has to stay at the same speed, so if you were to jump near a black hole, as you actually fell into a black hole, time would actually slow down, and it's crazy. If you were to look back behind you, you'd see the universe speeding up, actually. And so as the universe speed up, you would actually see the entire universe die as you were falling into a black hole. You would see billions and billions of years pass by in milliseconds because you're near a black hole. Say it again?
That's that way you consider our idea about time.
Yeah. So our time on Earth actually does move fairly slower because we're on a massive body. If you're near anything that has gravity, time will move slower for you. But Earth just doesn't have enough gravity to slow time down enough for us to notice it or care about it, okay? But if you were to go near a black hole, time would be really slow for you. Any other questions? Yeah? Oh, the EHT, yes. So how does the EHT telescope work? I'll very briefly describe it because it's kind of like magic to me, honestly. But basically, they use this thing called interferometry, where they take the light from a telescope in Antarctica, in Chile, in America, in Hawaii, and Japan, and they add up all the light together, more telescopes than that, but they add up all the light together, and that allows you to effectively have a telescope the size of the distance between each of those telescopes across the world. And that's called interferometry. It's very hard. It's like magic. I can barely explain it, honestly. But so if you take two telescopes and put them a mile apart and look at the same object, that telescope will actually turn into a telescope the size of a mile across. Okay? So it needed really high resolution. That gives you high resolution, interferometry, and high resolution. You needed very, very high resolution to see a black hole so far away, as well. Any limitations? Not really. It's just very hard to observe an object at the exact same time. That's the only problem. So they needed to record the data, actually, and ship the data across the ocean, and like terabytes and terabytes and terabytes of data to be able to make that image, which is amazing. Thank you for your question. Yeah, what in the back there?
Is there a way that non-astronomers and non-academics like us can assist with black hole research? Is there any citizen science projects?
Yeah, there are a whole bunch of citizen scientist projects that everybody in the community can help with. One of those is called Galaxy Zoo. So basically, you'd go on the internet, Google Galaxy Zoo, and they will show you images of galaxies, okay? And you can look through as many as you'd like. And you're going to tell the astronomers, what kind of galaxy is that? Is it a spiral galaxy? Is it an elliptical galaxy? Is it a regular galaxy? Are there gravitational lenses happening? Is there something interesting in the image? And you're going to let the scientists know what the galaxy looks like. In fact, they've published a ton of papers on this, and had I don't know if it's millions, but it's at least hundreds of thousands of people looking through these images, and you can help with that too through Galaxy Zoo as well. That doesn't. I'm not really associated with it. I just think it's really cool. Cool. Yes.
You already answered the question about the lifespan of a black hole.
Yeah.
But when you observe black holes that are billions and billions of light years away, can you tell whether they're still existing or not?
No. So the question was, even though we're observing black holes that are billions and billions of light years away, that means that we're observing galaxies that are very, very old. The light took a very, very long time to get to us. And so are those objects, because we're looking back in time, right? Are those black holes still around and kicking? Are they moving? We don't know. It's impossible to tell if those black holes are still around. We think that they are because it takes a really long time, like not just billions of years, but trillions of years for the most massive black holes to actually evaporate fully. It takes a very long time. It's some quantum mechanical effect I can explain to you if you'd like, but yeah. Okay, all right. He said no. I wonder why. So that's kind of, so we think they're still alive, but we're not sure because we can't see the light from, unless we moved all of Earth a billion years closer, light years closer, we wouldn't be able to tell. Did I see a question from a young gentleman? Yes.
Black hole kill you?
Oh. Question was, how can a black hole kill you? In many ways, my friend, in many ways, a black hole can kill you. One of those ways is that if you go near a black hole, there actually are tidal effects. So like how the tides work on Earth, tides will work on you, my friend. So what a tide is basically, a tidal force is, there's more gravity at your feet than at your head because your feet are closer to the main source of gravity. So that's happening to you now. Gravity is pulling you harder at your feet than at your head, okay? Because your feet are closer to Earth. The closer you are to something that has gravity, the harder you're going to feel its pull, okay? Near a black hole, it has so much gravity that actually, it's called spaghettification. You will get ripped apart because the forces at your feet are way stronger than the forces at your head. And so you'll actually be ripped apart, and then ripped apart again, and that's going to keep happening until you're just a stream of atoms falling into a black hole. All right? So sleep well tonight. There you go. There you go. Yeah. Cool. Do we have time for more questions? I heard sure, I think. So that's one of the ways. There are a couple more ways to die from a black hole. But yes, back in the back.
How is the distance measured?
Say that one more time.
How is the distance measured?
Ooh.
Black holes or stars?
Oh my goodness. So how is the distance to objects in space measured, especially to black holes? Well, there's this thing in astronomy called the distance ladder, where all of the distance measurements, they're kind of built upon each other. So the closest one that we use for planetary things is radar. So we shoot radar beams at Venus, and they come back, and we can measure the time delay, and we know how fast the speed of light is, and so we can tell how far away objects are. The next closest is parallax. So that's how we know the distance to stars in our galaxy. So if you hold out your thumb and blink your eyes back and forth, that's parallax, okay? And we do the same thing where Earth is June. There you go. The only one who did it. That's crazy. So you can think of the sun as your nose. Earth, your right eye is Earth in June, and your left eye is Earth in December, okay? And your thumb is the star. And we can measure that angle that it changes on the sky, and we know through simple geometry, simple, quote unquote, that how far away those objects are. The next closest one are called Cepheid variable stars. So these are types of stars that vary in brightness, and we know how much they vary in brightness based upon how intrinsically bright they are. And we can do some math to figure out their brightness. The next closest are supernovae. There are some specific types of supernovae that always explode at the same intrinsic brightness. And so you can have one of those stars exploding here and there, and if they have the same brightness, then you can tell basically how far away things are. Hopefully this isn't too complicated. The next one that we use for those quasars is called redshift. Okay, so if you measure how, it's a little complicated, but if you measure basically the change in color of an object in space, if it's far enough away, because the universe is expanding, okay, the universe is actually moving and actually accelerating too. But because the universe is accelerating, or it's moving apart, the light from those galaxies will appear to be more red, okay, in color. And if you measure how much more red it is, then you can tell how far away it is. But all those build off of each other. So we don't know the Hubble constant unless we know what those supernovae are doing. And we don't know how far away those supernovae are unless we use those variable stars. And if we don't know where those variable stars are unless we use parallax. And we don't know the closest star to us. We can't really use radar that far away. But so it's a ladder in the real sense. You have to build off of each other. So that is how a very brief lesson on how we tell distances in astronomy. Thanks for coming to my TED Talk. No, thank you. Yeah. I don't know what I do now. Okay. Oh, great. Thank you. Cool. Thank you.
All right, guys. Yeah, another big round of applause for our speaker tonight. Awesome, guys. So thank you for coming out to see and learn. Real quick, want to thank our sponsor. If you enjoyed the drinks and the food coming up, big round of applause for Shea Booba. Please make sure that you guys leave any of your glassware on that black table back there so they can collect it. And, well, myself, I understood absolutely everything that he said. But if you didn't, then you can meet with your speaker at Shea Booba and talk with him a little more. All right? Other than that, thank you for coming out, and we will see you guys next time.